Welcome back to the deep dive. Today we are tackling a subject that sits right at the jagged edge, where human language meets computer logic. It's the sort of thing that sounds intuitively easy to us. I mean, we do it all day long without thinking, but when you try to teach a machine to do it, you realize just how messy our brains actually are.
It is the ultimate paradox of AI. The things we find hardest, like calculus, computers do instantly. The things we find easiest, like understanding a simple sentence, computers struggle with immensely.
Exactly. We're looking at the difference between parsing a sentence, just knowing the grammar, and actually understanding its deep semantics, its logical soul. To do this, we are dissecting a fascinating paper titled Deep Semantics for Dependency Structures via Graph Rewriting. It's by Paul Bitteride and Claire Gardant from the University of Stuttgart and CNRS Laurea.
And their mission is, well, it's ambitious. They're proposing what they call a semantic calculus.
Calculus, that word usually makes people sweat.
In this context, think of it more like a rigorous mathematical framework. They want to take a web of words, a sentence, and physically transform it into a formal logic formula, first-order logic. The kind of math where there is zero ambiguity, no wiggle room, just pure truth or falsehood.
Which is the holy grail for AI right now, because we have these incredible large language models that can write poetry and code, but they're essentially statistical parrots. They guess the next word. They don't necessarily reason.
Right. They hallucinate because they don't have a grounding in logic. They don't have a truth model. This paper is proposing a bridge, a way to go from the messy surface of English grammar to the clean depth of mathematical logic.
So let's frame the big question for everyone listening. How do you teach a machine that two sentences which look completely different grammatically speaking might actually map to the exact same logical reality?
And conversely, how do you teach it that sentences which look almost identical might imply totally different things about the world?
The authors give a great example of this. John seems to love Mary versus it seems that John loves Mary. To you and me, those mean roughly the same thing.
Logically, yeah, they describe the same situation. There's a loving event involving John and Mary, and that event has a seeming modality applied to it.
But grammatically, totally different structures. So how do we get a computer to see past the grammar to the logic? To understand the solution, we first have to understand why our current tools are, well, not great at this. We need to talk about dependency parsing.
Right. This is the industry standard. If you use Google syntax tools or the Stanford parser, this is what you're using.
So paint a picture for us. When I feed a sentence into a dependency parser, what do I get back?
You get a dependency graph. Imagine a skeleton of the sentence. The words are nodes, little dots, and there are arrows connecting them labeled with grammatical roles. So in John loves Mary, you'd have an arrow from loves to John labeled subject and an arrow to Mary labeled object.
Simple enough. It tells you who acts and who is acted upon.
On the surface, yes. But the authors argue that these graphs are impoverished. They give you the syntactic geometry, what's next to what, but they lack deep information about semantic type.
Type meaning what kind of logical object the word represents.
Exactly. Let's go back to your example. John seems to love Mary. In a dependency graph, you have an arrow connecting seems to love.
Okay.
Now take, it seems that John loves Mary. In that graph, you also have an arrow connecting seems to loves. To the computer, just looking at those immediate links, the word seems appears to be doing the exact same thing in both sentences.
It just sees verb connected to verb.
Precisely. But logically, those are two very different operations. In the first case, John seems to love, the verb seems, is combining with the verb phrase. It's modifying the act of loving. In the second case, it seems that John loves Mary, the verb seems, is combining with an entire proposition. It's wrapping the whole fact that John loves Mary in a layer of uncertainty.
But the graph doesn't tell you that.
No, it doesn't. It just draws a line. To figure out the actual meaning, the computer would have to do what we call non-local lookups. It has to scan the graph, jump over nodes, and check, does the word love dominate a to or a that? It's inefficient. You're basically guessing the logic by acting like a detective in the grammar tree.
And grammar is notoriously messy. English is full of exceptions.
It is. And it gets even worse when we talk about scope. This is where the mismatch between the graph and the logic becomes a deal breaker.
The authors use a specific example for this, right? Which man does John think that Mary likes?
This is a classic linguist torture device. Think about the syntax there. Grammatically, man is the object of likes. Mary likes the man. So in the dependency graph, the word man is buried way down at the bottom of the tree, attached to the word likes.
But the question isn't about liking. The question is which man.
Precisely. Semantically, which man is an operator? It's the bucket that holds the whole sentence. It wraps around the entire thought. It's asking, identify the individual X, where X is a man, such that John thinks Mary likes X.
So the logical container of the sentence is which man. But in the graph, man is inside the container. It's inverted.
It's a total geometric mismatch. The syntax goes down, the semantics goes up. If you just translate the graph arrow for arrow into logic, you get nonsense. You fail to capture the scope.
So Baderide and Garden are saying, don't try to fix the graph, don't try to patch it, rewrite it.
Right. Enter the solution, graph rewriting. They use a tool called Gradient, the graph rewrite generator. The philosophy is semantics-driven. They treat the syntax graph not as the final answer, but as raw material like a lump of clay that needs to be reshaped into a statue.
But they don't just use the dependency graph, do they? They add another layer of input to help guide the chisel.
This is crucial. They combine the dependency graph with SRL semantic role labeling.
We need to unpack SRL. How is that different from just finding the subject and object?
Parsing tells you grammatical positions, subject, object. SRL tells you logical roles, agent, the doer, and patient, the receiver. Or more abstractly, arg and arg1.
Why does that distinction matter?
Because grammatical positions change, but semantic roles stay the same. In John broke the window, John is the subject and the agent. But in the window was broken by John, the window is the subject, but John is still the agent.
Ah, I see. So SRL gives the system a stable anchor point regardless of how I phrase the sentence.
Exactly. So the input to their system is this combined supergraph, words, grammatical links, plus these semantic role tags.
Okay, we have our raw material. Now, the authors propose a 4-step assembly line to build the logic formula. I love a good step-by-step process. Let's walk through it.
Let's do it.
The example they use is the classic logic test. Every man loves a woman.
A deceptively simple sentence.
Right, because of the quantities. So step 1 is the creation of seed nodes. What on earth is a seed in this context?
Imagine the system scanning that input graph. It ignores the fluff words that don't carry heavy meaning. It looks for the content words, the predicates and arguments. It sees loves, man, woman. It plants a seed node for each of these in a new, empty semantic graph.
So we literally start with 3 dots floating in the void.
At this stage, yes, they're just empty placeholders. But then comes step 2, node expansion. The seeds start to grow based on what they are.
This is where the specific words matter. Every versus a.
Exactly. The system sees the phrase every man. It knows every is a trigger for a universal quantifier. So it doesn't just leave the man seed as a dot. It expands it into a complex little tree structure, a generalized quantifier.
Can we visualize that tree? What does it look like?
Imagine a root node. Hanging off it are 3 branches. One branch is the quantifier itself, the symbol for all. The second branch is the restriction, X is a man. The third branch is the scope, what happens to that man.
Okay, so man becomes this tripod structure. What about a woman?
The system sees a, or an, and knows that triggers an existential quantifier. The symbol for there exists, it builds a simile tripod structure. There exists a Y, where Y is a woman.
And the verb loves.
This is interesting. In modern logic, we treat verbs as events. So the love seed expands into an event variable. It says, there exists an event E, and E is a loving event.
So now we have 3 separate little trees, a universal tree for man, an existential tree for woman, and an event tree for love. But they aren't talking to each other yet. They're just islands.
That brings us to step 3, specifying scope. We have to link these structures together. We have to decide who eats whom. Does every man cover a woman, or does a woman cover every man?
This is the famous ambiguity. Every man loves a woman could mean every man loves his own specific partner, or it could mean every man loves Beyoncé, one specific woman loved by all.
Humans struggle with this context, but for this system to keep it computational and robust, the authors make a simplifying assumption. They assume scope is determined by the linear order of the words.
First come, first served.
Basically, since every man appears first in the sentence, the system draws a link, making it the dominant scope. It swallows the next quantifier. So the man tree wraps around the woman tree.
Is that safe? I mean, English is pretty flexible. What about a woman is loved by every man?
In that case, a woman comes first, so she would take scope. There exists one woman, and every man loves her. It works for a vast majority of standard English constructions. It's a heuristic, a rule of thumb,
Right.
but it prevents the system from crashing into an infinite loop of indecision.
Okay, so we have the hierarchy. Man over woman over love. But we still haven't actually connected the variables. We haven't said who is doing the loving.
That is step 4, specifying predications or binding variables. This is the fine detail work. This is where the system uses those semantic role labels we talked about earlier.
The agent and patient tags.
Right. The system looks at the loves event structure. It has an empty slot for agent and an empty slot for patient. It checks the input graph. Okay, the SRL says man is the agent. So it takes the variable $6 from the man tree and plugs it into the agent slot.
And it takes the $1 from the woman tree and plugs it into the patient slot.
Exactly. And notice what didn't happen. The system didn't care about the word order for this part. It didn't care if it was passive voice. It didn't care about the grammar. It just trusted the semantic roles.
That is really smart. It separates the who is in charge scope from the who did what binding.
That separation is the key innovation here. It allows the system to be robust. You don't need a million rules for every grammatical exception. You just need rules for how to handle the semantic roles.
Speaking of exceptions, the paper does stress test this. They don't just stick to John loves Mary. They look at relative clauses. John loves a woman who sings.
The nightmare of the word who.
Right. In a syntax tree, sings is attached to who, but logically who is a ghost. It isn't a person, it's just a pointer to woman.
And this is where relying on the semantic role labeling saves the day again. In the SRL input, the system typically resolves that link before the rewriting even starts. The SRL connects sings directly to woman.
So the who is essentially bypassed.
Effectively, yes. When the graph rewriting rules run, they just see woman as the agent of sings. It treats woman who sings exactly the same as singing woman. The structure becomes uniform.
What about control verbs? This is one of those linguistic terms that sounds scary but is actually pretty common.
It's intuitive. Compare John promised Mary to shave versus John persuaded Mary to shave.
Okay. In the first one, John promised that he would shave. In the second, John persuaded Mary so that she would shave.
Right. But look at the word order. Mary is right next to shave in both cases. A dumb parser might assume Mary is always the shaver because she's closer to the verb.
But the SRL knows better.
The SRL knows the difference between a promise, which is subject control, and a persuasion, which is object control. It labels the arguments correctly before the graph rewriting begins.
So the rewriting system, the calculus, doesn't need to know English grammar quirks. It creates the logic based on the labels.
It abstracts away the messiness. It says, I don't care how you phrased it, the label says Joan is the shaver, so variable $6 goes into the shaving slot.
It feels like they are shifting the burden. The genius isn't just in the rewriting, it's in relying on high-quality semantic role labeling.
That is a fair critique. The system is only as good as its inputs. If the SRO gets it wrong, the logic will be wrong. Garbage in, garbage out.
Well, let's talk about the output then. Did it work? They didn't just write this on a napkin. They tested it on 1,000 sentence pairs using entailment recognition.
Right. Entailment is the gold standard for understanding. It asks, does sentence A mathematically imply sentence B?
Like, John bought a car implies John owns a car.
Exactly. Or every man loves a woman entails a man loves a woman. They ran this on the Fricas test suite, which is a standard data set for these logical puzzles. First off, and this is significant, the system successfully generated a logic formula for 100% of the sentences.
It didn't crash.
It didn't choke on complex syntax. That's a win for the robustness of graph rewriting.
And the accuracy. Did it get the entailment right?
It got 71.3% accuracy.
71%. Is that good? If I got a 71 on my calculus exam, I wouldn't be bragging.
In the context of deep semantics from raw text, it's actually quite promising. You have to remember, they're competing against systems that often use lambda calculus.
The authors mention lambda calculus a few times as the rival approach. Why is that the alternative?
Lambda calculus is the rigorous, traditional mathematical way to do semantics. It's beautiful, but it's brittle. It builds meaning by strictly following the syntax tree, node by node, combining them in a rigid chain.
Like a fragile glass chain.
Exactly. If the syntax tree has one weird quirk or one parsing error, the whole chain snaps, the derivation explodes, and you get nothing. The graph rewriting approach is more like finding a path through a web. If the parser makes a small mistake, the graph rewriting rules might still find a valid path to a formula. It's tolerant of noisy input.
And the errors they did find, the 29% that failed, where did those come from?
Mostly from the pre-processing. The dependency parser gave a wrong link, or the SRL identified the wrong agent. The logic machine worked, but the raw materials were flawed.
So if parsers get better, which they are every year, this system gets better for free.
Exactly. It scales with the quality of the entire AI ecosystem.
I want to zoom out a bit. Why should a listener who isn't a computational linguist care about this? We have ChatGPT. It seems to understand us fine. It can write emails, summarize articles. Why do we need this first-order logic stuff?
Does ChatGPT really understand, though? Or is it just a very sophisticated parrot? The problem with current AI is the black box. You ask it a question, it gives an answer, but you cannot trace the steps. You can't see the logic.
It's probabilistic, not logical. It feels right, but it might be wrong.
Right. This paper proposes a way to turn text into explicit logic. If you can convert a legal contract or a medical guideline or a privacy policy into first-order logic, you can use an automated reasoner, a theorem prover, to check it,
You could mathematically prove that a contract has a loophole.
or prove that two medical instructions contradict each other. You can't do that reliably with a large language model because it's just guessing words. You need the symbolic representation.
It's like the difference between painting a picture of a bridge and actually building the blueprints. The LLM paints the picture. This system builds the blueprints.
That's a great analogy. If you want to build a bridge that doesn't collapse, you need the blueprints. And the authors see this extending further. They want to handle comparatives, John is taller than Mary, and discourse connectives like if, then.
If the alarm goes off, then open the door.
Exactly. Handling that logic across multiple sentences is the next frontier. Imagine an AI that can read a whole user manual and build a consistent logical model of how a machine works.
That's powerful. It moves us from chatbot to reasoning engine.
It validates the idea that structure matters.
Yeah.
We can't just treat language as a stream of tokens, a bag of marbles. There is a deep, hidden structure, a graph that holds the meaning. We just need the right calculus to decode it.
So let's recap this journey because it's a lot to take in. We start with a sentence. It gets parsed into a dependency graph, a web of words.
Which gives us the skeleton.
We add semantic role labeling to identify the players, the agents, and patients.
Which gives us the anchors.
We use graph rewriting to plant seeds for the concepts.
We expand those seeds into logical trees, quantifiers, and events.
We link them up based on word order to handle the scope who dominates whom.
And finally, we bind the variables using the semantic roles, ignoring the messy surface grammar.
And out pops a formula that a computer can truly mathematically understand.
That's the pipeline, from text to truth.
It really highlights how much unconscious processing the human brain does. We do all those 4 steps in milliseconds without thinking about it.
And we're trying to externalize that process into code. It's incredibly difficult, but this paper suggests we're getting the right abstractions in place.
Here's a thought to leave you with. If we can get this accuracy up, if we can reliably turn natural language into logic, does that solve the trust issue in AI?
It certainly helps. If an AI can show you its work, I believe X because of Formula Y, that is a game changer for critical applications. It's the difference between, trust me, I'm an AI, and here's the proof.
Explainable AI via graph rewriting. It's a dense topic, but a crucial one for the future of thinking machines.
Absolutely.
Thanks for diving deep with us. Keep questioning the black box, and we'll see you on the next one.